Greetings. This is the creator of Grassmann.jl speaking. The purpose of this presentation is to provide an overview of some of the computational algebraic foundations with which I'm researching mathematics. The journey starts with Julia and the terminal. Julia is a programming language which is supported on every major operating system. So we can type Julia in the terminal. It's possible to install the Grassmann.jl package by using the command add Grassmann in the package manager. We already have the package installed here at the moment, so we can just type using Grassmann. So there we go, the package is loaded. It loads fairly quickly. It's comparable to the static arrays package in terms of loading time. But it doesn't actually depend on the static arrays package itself. So this is entirely its own linear algebra engine. It's based on the Grassmann algebra. And so the way it works is we're all familiar with the three-dimensional space that we're typically used to in linear algebra, and we can obtain that using the basis 3 command. And this generates a three-dimensional basis in terms of the Grassmann exterior algebra basis in the local workspace. And so now we can use the algebra like V1 times V2 to take the geometric product, or V1 wedge V2. And the way we get this wedge is by using the backslash and then typing wedge and then pressing the tab key. This is how we can get these type of Unicode characters. So there are many types of algebras that can be generated with Grassmann. We're just going to take a look at the moment at the basic three-dimensional algebra because many people are familiar with that already, and it makes an easy example to talk about at the beginning. So there are a huge amount of algebraic and computational methods directly available with Grassmann.jl. At the time of this video, I've not had time to update all of the documentation, so I'm making this a quick overview video right now, a bit spontaneously. I have several other presentations in the past about the concepts which Grassmann.jl is based on, and in this particular video, a casual familiarity with geometric algebra is assumed as a motivation for watching the video. Grassmann.jl is not a new project. It has been around for many years, and I was thinking of it long before I started working on it. When I started this project, everything about my approach was about meticulously innovating computational language design from the ground up. This video is a bit spontaneous and unplanned, but the computational language design featured in the video has been under systematic development for years. So we've now established a three-dimensional basis that we've assigned into our workspace here using the Grassmann exterior algebra. And so what's the significance of this? Why was I interested in this? Well, in the Julia language, there was this built-in complex number type in the programming language, complex number type basically, and it has implemented in basically the Julia language itself. It's not implemented in terms of some kind of lower level C language or something else. The source code is written in plain Julia code, the same type of plain Julia code that I as a user or you as a user of the Julia language could use. And so I thought, what if I make my own complex number type but generalize it to the full Grassmann algebra? And here we go. That's what I ended up with. So we have the exponential function, just like for complex numbers. You can exponentiate the bivector, for example. And we can get these different results. And of course, what a lot of people find interesting about geometric algebra is the sandwich product. And so if we apply this operator using the sandwich product, which I call O/ in the programming language, then it transforms, for example, the basis vector v1 to the basis vector v2. And the basis vector v2 transforms to minus v1. And this additional number here, this is 0. This is just a number that's very small, close to 0, due to the numerical calculations involved. And that's the sandwich product. And of course, this is the convention that I find preferable, is having the operator on the right side. But a lot of people prefer using the operator on the left side instead. And that convention is supported as well. And of course, that has the reverse compositional property, and instead of the O/, which is the symbol I used, this is the triple arrow symbol, basically, which can transform the basis in the same way, but just with a different convention of the sandwich operator formalism, basically. And this is the one that people are more typically familiar with in other literature, but this is, I believe, the more correct Euler convention. So that's just kind of a conventional choice, but the point is that you can apply the sandwich product and it works like an outer morphism. So if you apply it to a grade 2 object, it works like that. So that's just how it works. And for convenience, we provide the endomorphism representation like this. And we can see that if we change the angle of the operator, we get different kind of endomorphism representations. Now, what else is it that we can do for casual geometric algebra convenience? If you're interested in getting the Cayley table of this particular geometric algebra, so first of all, V is the kind of vector space that was used to generate this basis. And so when this basis command is executed in the Julia terminal, then the V variable is assigned a object, which is basically the vector space representation of that geometric algebra. And so if we ask it for the Cayley table of that V, and we specify the product operation to use, such as the wedge product, then it's outputs the Cayley table using an endomorphism representation. And we can compare that with the regressive product, and we can use the dot product or interior product contraction, and we can use the geometric product as well. And this helps provide an overview of what this particular algebra acts like. So you can do that for different algebras depending on what V is, basically. So that this is just an example for three-dimensional Euclidean algebra, but Grassmann.jl supports the fully general metric. So what are some of the other kind of metrics that you can generate algebras for? So for example, we could generate a metric using this plus or minus signature. This is an example. You can, choose entirely your own sequence of pluses and minus. And some people have different preferences about what they prefer in terms of signature of a metric. And so this basis generation procedure allows you to choose which index has a plus or a minus signature. So V1 times V1 is negative, and V2 times V2 is positive. And that's because we put the minus sign into the first, signature position. But this is fully general in terms of allowing you to choose any sequence of pluses and minuses in any order that you want. It's not just that the minuses have to be at the beginning or end or something, or you could put a minus in between if you want, and it just lets you do whatever you want in terms of the signature. And if that doesn't satisfy you, you can also generate a diagonal basis, diagonal form basis, and you can use the D constructor, for example. We can put 4, 5, 6 as the metric. And what does this mean? Now the element V1 times V1 squares to 4, and V2 times V2 squares like that, and V12 times V12 is negative 20. So it lets you go fully general in terms of the diagonal metric. Or you can, if you want to change to a different kind of a metric tensor in the fully general sense, you can, for example, rotate these two basis components in the way that the conformal geometric algebra basis is formed. And then we have V1 times V2 is equal to what? Minus 1 plus V12. So this is because the metric is now not a diagonal metric anymore. So this is a non-diagonal metric. So let's take a look at the metric tensor of V. So if we take a look at the diagonals of this metric tensor, some of them are 0, and now these are off diagonals. So now we've transformed the metric tensor into a different kind of basis, and now the geometric algebra responds differently as a result of that different metric tensor and how the geometric product combines elements together. And it also affects the interior product and the Hodge complement, and the whole entire Grassmann algebra is entirely affected by the metric tensor and how it's defined. So that gave us kind of a basic presentation that we can generate different algebras with different properties that transform the basis elements in different ways when you combine indices and contract them and so on using the metric tensor. And Grassmann.jl is one of the most advanced libraries available for geometric algebra. It is able to do calculations with standard space-time algebras and also much higher dimensional algebras as well, at dimensions where other libraries would get stuck or crash at a compilation error. Although such high dimensional algebras are only really a curiosity for me, the real interest for me is in like the medium to lower dimensional algebras in applied mathematics, basically, in the engineering and physics and so on. So what is some of the language design that has resulted in having the Grassmann geometric algebra in the Julia language? Well, I have a abstract type called TensorAlgebra. And it allows us to look at different subtypes of the tensor algebra. And this is still a work in progress and development, the whole type hierarchy. For Grassmann.jl itself, it's roughly a complete type hierarchy, but there might be other kinds of tensors that can get added to it in the future and that might get changed around or whatever. And we'll find most of them under the subtypes of manifold at the moment, although the name manifold could change in the future. At the moment, that's what I picked at the time because it worked at the time, but we'll see how things evolve still before the version 1.0 release. And here what we really are interested in is the subtypes of tensor graded. So for tensor graded, we have the chain and the tensor term. And tensor term is again an abstract type, which contains, the zero, the submanifold, the single, the infinity. So there are many different kinds of types that might show up in. So these aren't even all the types that I've shown you so far. We've just kind of zoned in down one branch of the type tree, actually. So this is just one branch of the type tree that we're kind of digging deeper into. And we found a lot of different types here, and this isn't even all of them yet. And so I have this kind of type hierarchy, a type tree, and this helped. I mean, you don't necessarily need to know that much about this type tree, although the more you learn about it, if you want to if you're sincere about using this package, then learning about the different types will of course give an advantage to you because you'll be able to make better use of it. But you don't necessarily have to learn about these things just to use the package, because just to use the package, you can just generate a basis like the three-dimensional basis and interact with the basis elements to construct new elements from those. You know what I mean? So like if you take the sum of these two bivectors, you get this object as a result. And then if you add, the trivector to that, you get the multivector. And a multivector we need to leave out that space there. The multivector is a full assignment of every, tensor every combinatorial, tensor combination, because this basis has 8 possible indices or arrangement of indices modulo the orientation, and the orientation is of course part of the coefficients, like the number, like this number 1 tells us that this is the basis element we're representing. And there are different types in the algebra, such as, for example, the submanifold. So let's just dump this here. This is a submanifold. This is one of the fundamental types in Grassmann.jl. Any of these, basis elements is a submanifold, which helps. It's a very fundamental part of the design. I won't get into it too much in this overview video, but in terms of the design itself, it's a very deep, fundamental, philosophical design point of the computational language design that I've developed over the years. But if we add a coefficient to a basis element like 1.23 v123, now we have a single. Single means there's a single coefficient, and then there's the value of it associated to the basis element, basically, using the type system. And that's just, that's what's called a single. And now if you, exponentiate a bivector, that's a couple. Because a scalar plus a bivector is what I call a couple. In terms of naming things, I call this a couple. And like if you take the complement of that, what you get is a pseudo couple, which is a pseudo scalar plus, in this case, it's a vector basis element. But that's basically the complement of the couple exp of v12. Basically, complement of it would be this pseudo couple. And so that's called a couple. This is a pseudo couple because it involves the pseudo scalar. So this is kind of a fundamental new design point that I am investigating in this computational language design. We've also got the spinor type, of course. If we take a bivector and we convert it to a full spinor in 3-dimensional algebra, this would have 4 values. This would be like a quaternion, what you are typically familiar with in other literature. You would call this a quaternion, although the orientation of the basis might slightly depend on what you define as 1 3, because typically you would have 3 1, you would have minus v1 3. Basically, you would have the orientation of that reverse in terms of quaternion. But if you want to represent it in terms of this basis here, this is how you would get it. And of course, spinor v13 would be oriented in this way, but there is a quaternion, or what is it? Quat values, I believe, quat values that returns the v13 oriented, correctly. The v12 would stay the same, but the v13 would be oriented. So if you wanted to get the values oriented, like the quaternion values like that, out of the spinor value, you could do it like that. That's just a convenience function. I mean, it's nothing complicated. There's much more interesting conveniences built into Grassmann.jl, but this is just kind of a basic overview of some of the things that you can do for convenience with, the basic algebras that we are familiar with. So yeah, over the years, I've experienced a lot of interesting ideas with geometric algebra, and I implemented a lot of additional features in the Grassmann.jl package. And the purpose of this presentation is just to provide a kind of basic overview of some of the computational algebraic foundations with which I'm researching mathematics. And keep in mind, this Grassmann.jl algebra is a foundation with which it's possible to build all sorts of other research. And so this is a computational language design that helps me think about mathematics in higher dimensions. This is just what I prefer. Many other people have worked with the traditional formalisms of, programming mathematics using whatever programming language or in the Julia language. I've also, worked with the Wolfram language in the past as well. I've been at their Wolfram summer school, and I've worked there as a teaching assistant, and I mainly focus on this Julia language implementation at the moment because I'm very interested in the numerical computation capabilities, and the code generation for numerical computation in the Julia language was quite intriguing to me. And this is what it allowed me to come up with in terms of language design, in terms of coming up with a way of interacting with the Grassmann geometric algebra using computational language. And that's what this was about for me, so that I can intuitively play around with this algebra and do different kinds of things with it at a fairly good, computation performance using my equipment at home here, researching mathematics. And that's just what it was about for me. So I am fundamentally an introvert, and I am basically writing this computational language design software open source on the internet because this is just what I'm doing as part of my introverted nature over a decade of being interested in mathematics. And I'm not doing this to particularly attract attention for doing this, although I would like people to recognize that I have been out here doing this for some time, that I have dived really deep into these concepts and done a pretty good job of implementing them in computational language. And I'm not doing that just to get some kind of attention for it, but I do hope I would like people to recognize in this space of computational language that I'm here doing this thing, and that this is what I'm studying mathematics with. So this is just a little glimpse. There's a lot more interesting things I'd like to show that can be done with Grassmann.jl, but but those things will have to be shown when the time is ready for that. And I'm going to return to my introverted studies of, researching different kinds of mathematics, not just geometric algebra. I am exploring many kinds of mathematics out here in the realm of numbers and different kinds of theorems. I am not just interested in geometric algebra by itself. I'm interested in applied mathematics and all kinds of other pure mathematics. And so this is just one aspect. I've released other packages in the Julia language, other software. I've done other things. I've researched other things. I've done things besides mathematics. I've been interested in music production and synthesizers, and I was interested in many different things. This was one of those things that interested me, and I happen to have done a really good job at it, that it resulted in useful software that, I think it's very useful, and I think there's some other people who would agree that this is a interesting, powerful way of algebra and computational mathematics.